Hello there, and welcome to Science for Sleep, where curiosity gets comfortable and science unfolds at an unhurried, gentle pace. Tonight, we're going to wander far beyond the familiar planets of our own solar system and drift outward into the enormous dark between the stars, where astronomers have discovered worlds so strange, so intense, and so different from anything we know that they almost seem imagined rather than real. Before we get there, take a moment to settle in. Let your shoulders loosen a little. Let the day move a step farther behind you. There's no rush here, and nothing you need to keep track of. Just listen, and let your thoughts slow to the rhythm of the voice you're hearing now. Out there, scattered across our galaxy, there are planets where the ground may be molten rock glowing red under skies that never cool. There are planets so close to their stars that their atmospheres are being blown away into space, stretched behind them like long invisible tails. There are planets that wander alone in darkness, with no star at all, drifting silently between the constellations. And there are worlds where storms rage with winds faster than any hurricane on Earth, where temperatures could melt metal, and where gravity itself would feel unfamiliar beneath your feet. It's strange to think that just a few decades ago, we didn't know whether planets around other stars even existed. The night sky looked full, yes, but also quiet and distant, as if our solar system might be a rare island in a vast ocean of emptiness. Now we know that planets are everywhere. Thousands have already been found, and scientists suspect there may be hundreds of billions in our galaxy alone. And among all those distant worlds, some stand out as the most extreme places ever observed. They stretch our understanding of what a planet can be. They challenge the assumptions we grew up with, the quiet idea that planets should be calm, solid, and predictable places like Earth or Mars. Instead, they reveal a universe that is inventive, unpredictable, and sometimes almost absurd in the environments it produces. But before we travel too far in our imaginations, let me ask you something gently, the way one might ask a quiet question while sitting beside a window at night. Where are you listening from right now? And what time is it in your corner of the world? Perhaps it's late evening and the lights outside your window are thinning. Perhaps it's early morning and the sky's still dim, with the first hint of dawn somewhere behind the rooftops or trees. Wherever you are, whatever hour the clock might say, it's interesting to remember that time itself feels different depending on how we spend it. A few minutes of waiting can feel long, but time spent drifting through an idea or listening to a story can pass almost unnoticed. If you find this journey soothing or simply interesting in a quiet way, I'd be grateful if you gave the video a like and perhaps subscribe to the channel. It helps this calm little space reach other listeners who might be looking for the same kind of gentle curiosity at the end of their day. But for now, there's nothing to do, nothing to click, nothing to keep track of. Just listen. Now imagine for a moment that you are standing under a perfectly clear night sky, far from city lights. Above you, the stars appear steady and serene, small points of light scattered across an enormous darkness. To the eye, they look peaceful, almost unchanging. Yet each of those stars is a sun, often larger and more powerful than our own, and many of them are surrounded by planets moving in silent orbits, worlds we cannot see directly, but whose presence we can detect through careful observation. Some of those planets are calm, perhaps even Earth-like, places where temperatures might be gentle enough for oceans or clouds. Others, though, are anything but calm. Some orbit so close to their stars that a year there lasts only a few hours. Others swing in long, stretched paths, freezing and scorching in turn as they travel around their suns. A few are so dense that a person standing on their surface, if such a thing were possible, would feel their own weight multiplied several times over. And that raises a curious thought. When we imagine planets, most of us instinctively picture something familiar. Solid ground, a sky overhead, perhaps oceans or mountains. But the universe isn't obligated to follow our expectations. A planet, in the simplest sense, is just a world that orbits a star and is large enough for gravity to shape it into a sphere. Beyond that, the possibilities open up in ways that are almost endless. There are planets made mostly of gas, like Jupiter, where there is no solid surface at all, only deep layers of cloud and pressure. There are planets that may be composed largely of water, with oceans hundreds or thousands of kilometers deep, far deeper than any sea on Earth. There may even be planets where the chemistry of the atmosphere produces clouds of substances we would find toxic or unimaginable here at home. And yet, despite all this variety, it took us a surprisingly long time to confirm that such worlds existed beyond our solar system. For most of human history, planets were known only as the few wandering lights visible in our own sky: Mercury, Venus, Mars, Jupiter, Saturn. Uranus and Neptune came later, discovered with telescopes. But beyond those, there was only speculation. Astronomers suspected that other stars might have planets, but the problem was one of scale and brightness. A star is dazzlingly bright compared to a planet. Trying to see a distant planet next to its star is a bit like trying to spot a firefly beside a lighthouse from thousands of kilometers away. The light overwhelms the view. So instead of seeing the planets directly, scientists learned to look for subtler clues. They measured the tiny wobble of a star caused by the gravity of an orbiting planet tugging on it. They observed the faint dimming of a star's light when a planet passed in front of it. These methods required patience, precision, and instruments sensitive enough to detect changes that were almost unimaginably small. When the first confirmed exoplanet around a Sun-like star was discovered in the 1990s, it was a moment that quietly reshaped our understanding of the universe. Suddenly, planets were no longer theoretical possibilities. They were real, measurable, and waiting to be found in enormous numbers. What surprised astronomers most, however, was not just the existence of these planets, but how strange many of them were. The earliest discoveries included massive gas giants, orbiting extremely close to their stars, far closer than Mercury orbits the Sun. According to earlier theories of planet formation, such arrangements seemed unlikely. Yet there they were, undeniable, circling their stars in a matter of days. It was the beginning of a realization that would grow stronger with each new discovery. The universe is not limited by our expectations. Planetary systems can arrange themselves in ways that feel unfamiliar or even counterintuitive. Orbits can be tilted, stretched, crowded, or chaotic. Planets can migrate inward or outward over time. Entire systems can evolve in ways that are difficult to predict from first principles. And somewhere among all these possibilities lie the most extreme worlds ever found, places where temperature, gravity, weather, and chemistry reach conditions far beyond anything on Earth. One of the quiet pleasures of learning about these worlds is that they expand our sense of what is possible. They remind us that our planet, comfortable and familiar as it feels, is just one example among many. Earth is not the template for all worlds, but a single variation in a vast cosmic catalogue. It's also worth pausing to notice something else. Even though these planets are unimaginably distant, sometimes hundreds or thousands of light years away, the light we use to study them is reaching us now in this moment. Photons that left those stars long before modern civilization existed are arriving at our telescopes tonight, carrying tiny signatures that tell us about atmospheres, temperatures, and orbits. In a sense, every discovery is a message that has been travelling through space for centuries or millennia, finally arriving in the quiet of an observatory. There is something calming about that thought. The universe is vast, yes, but it is also patient. Processes unfold over millions or billions of years. Stars form, shine, and fade. Planets cool, shift, and sometimes vanish. And here we are, brief observers, learning to read the faint traces of those distant stories. Long before astronomers could speak confidently about scorching lava worlds or giant planets whipping around their stars in a matter of hours, there was a quieter, more uncertain period, when the very idea of planets beyond our solar system was still being debated. For centuries, people wondered whether other stars might host worlds of their own. But wonder alone is a fragile thing in science. It needs evidence, something measurable, something repeatable, something that doesn't vanish the moment you look at it too closely. If you step back for a moment and picture the challenge, it becomes easier to understand why this took so long. A planet does not shine with its own bright light the way a star does. It reflects only a small fraction of the light it receives. Even Jupiter, enormous as it is, would be almost invisible from far away beside the sun's glare. Now imagine trying to detect a planet orbiting a star dozens or hundreds of light years away. The star outshines the planet by thousands or even millions of times. It is not merely difficult to see the planet directly. For a long time, it was essentially impossible. So astronomers began to think in a different way. Instead of trying to see the planets themselves, they asked a quieter question. What effects would a planet have on its star? If a planet is orbiting, gravity is pulling in both directions. The star is far more massive, of course, but it does not remain perfectly still. It moves slightly, wobbling back and forth in response to the planet's pull. This motion is extraordinarily small, but it is not zero. And in that tiny motion lies the key to one of the earliest and most successful methods of finding exoplanets. Imagine watching a distant star through a powerful telescope, night after night, year after year. At first glance it appears steady, a fixed point of light. But when astronomers examine its light with spectrographs, instruments capable of measuring subtle changes in wavelength, they can detect something remarkable. As the star moves slightly toward us, its light shifts a little toward the blue end of the spectrum. As it moves slightly away, the light shifts toward red. This is known as the Doppler effect, the same principle that causes the pitch of a passing siren to change as it moves by. By measuring these shifts with extraordinary precision, astronomers can detect the presence of an unseen companion tugging on the star. From the pattern of the wobble, they can estimate the planet's mass and the length of its orbit. It is a method that requires patience and meticulous observation, but it has revealed many worlds that would otherwise remain hidden. The first confirmed detection of a planet orbiting a sun-like star using this technique came in 1995. The planet known as 51 Pegasi b turned out to be something few scientists had expected. A gas giant orbiting extremely close to its star, completing a full orbit in just over 4 days. It was hotter than any planet in our solar system, and its existence forced astronomers to reconsider long-standing theories about how planets form and move. That discovery was a turning point. It showed that exoplanets were not only real, but that they could be very different from the orderly arrangement of worlds we were familiar with. And once one planet had been found, astronomers knew there must be many more waiting to be discovered. At the same time, another method was quietly proving just as powerful, though it required a different kind of observation. Instead of watching a star's motion, astronomers began watching its brightness. Picture a distant star as a tiny, steady lamp. If a planet passes in front of it from our point of view, the planet blocks a small fraction of the light, causing the star to dim ever so slightly. The change might be less than 1%, sometimes far less, but with sensitive instruments, it can be detected. This technique, called the transit method, has become one of the most productive ways of finding exoplanets. When a planet transits its star repeatedly, astronomers can measure the timing and depth of the dips in brightness. From this, they can determine the planet's size, its orbital period, and sometimes even details about its atmosphere. The transit method works best when large numbers of stars are monitored simultaneously, because only a small fraction of planetary systems are aligned in such a way that transits are visible from Earth. To accomplish this, space telescopes have played a crucial role. One of the most influential was the Kepler Space Telescope, launched in 2009. Kepler stared continuously at a single patch of sky, monitoring the brightness of over 150,000 stars. Night after night, Year after year, it recorded tiny fluctuations in starlight, searching for the telltale dips that might signal a planet passing in front. The patience of that mission is almost soothing to think about. For years, Kepler simply watched, quietly collecting data, waiting for patterns to emerge, and emerge they did. Thousands of candidate planets were detected, and many were confirmed. Some were small and rocky, closer in size to Earth. Others were giants, larger than Jupiter. Some orbited close to their stars, others farther away. Kepler transformed our understanding of the galaxy. It revealed that planets are not rare exceptions but common features of star systems. Statistically speaking, most stars likely have at least one planet. Many have several, and yet even these methods do not always give us the full picture. Measuring a planet's size or mass is one thing. Learning about its atmosphere, its temperature, or its weather is another challenge entirely. To do that, astronomers began to use another subtle trick. When a planet transits its star, a small amount of starlight passes through the planet's atmosphere before reaching us. Different gases absorb different wavelengths of light, leaving faint fingerprints in the spectrum. By analysing these patterns, scientists can identify the presence of elements and molecules such as hydrogen, sodium, water vapour, or methane. It is a delicate measurement, almost like trying to determine the ingredients of a distant soup by analysing the steam rising from it. But with modern telescopes it has become possible, and the results have opened a new window into the nature of distant worlds. There are other methods too, each with its own strengths. Gravitational microlensing, for example, relies on the way gravity bends light. When a star passes in front of a more distant star, its gravity can act like a lens, magnifying the background light. If a planet is orbiting the foreground star, it creates a brief additional brightening, a small ripple in the light curve that reveals its presence. This technique is particularly useful for finding planets far from their stars, including some that might otherwise be difficult to detect. It has even revealed planets that appear to drift freely through space, no longer bound to any star. Another approach, direct imaging, has begun to produce results as well, though it remains challenging. By using special instruments that block out a star's glare, astronomers can sometimes capture faint images of large planets orbiting at great distances. These planets are often young and still glowing with residual heat, making them easier to see in infrared light. It's remarkable to consider how much ingenuity has gone into these discoveries. Each method required not only advanced technology, but also new ways of thinking about what to look for and how to interpret subtle signals buried in noise. And all of this work has been carried out across decades by teams of scientists carefully analysing data, refining techniques, and cross-checking results. Discovery in astronomy rarely happens in a sudden flash. More often, it unfolds gradually, as evidence accumulates and patterns become clear. There is also something quietly reassuring about the precision involved. The instruments used to detect exoplanets must measure changes in starlight so small that they would be imperceptible to the human eye. A wobble of a few meters per second in a star hundreds of trillions of kilometers away. A dip in brightness smaller than the shadow of a tiny insect crossing a distant lamp. These are the scales at which astronomers work. It reminds us that the universe often reveals its secrets, not through dramatic events, but through careful observation and patience. As the catalogue of known exoplanets grew, another realization began to take shape. The variety of planets being discovered was far greater than anyone had anticipated. Worlds larger than Jupiter, orbiting closer to their stars than Mercury does to the Sun. Planets with densities suggesting they were made largely of iron. Others so puffed up and low in density that they seemed almost like enormous balls of hot gas barely held together by gravity. Each discovery added another piece to the puzzle, and gradually a new picture of planetary systems began to emerge, one that was more diverse and dynamic than the tidy diagrams in old textbooks. At the same time, improvements in telescope technology, both on Earth and in space, continued to expand our reach. Instruments became more sensitive, data analysis techniques grew more sophisticated, and new missions were planned with the specific goal of studying exoplanets in greater detail. Today, telescopes like the James Webb Space Telescope are capable of analysing the atmospheres of distant planets with unprecedented precision, detecting molecules and measuring temperatures in ways that would have seemed impossible just a generation ago. All of this progress has brought us to an interesting moment in the history of astronomy. We're no longer asking whether planets exist around other stars. We're asking what those planets are like, how they formed, how they evolve, and how extreme they can become. Because as astronomers began to look more closely, they found that some of these worlds are not merely different from Earth, but radically so. Planets where the conditions stretch the limits of physics and chemistry as we know them. Places where temperatures soar to thousands of degrees, where winds race faster than sound, where entire atmospheres are stripped away by stellar radiation. When astronomers describe a world as extreme, they are not usually speaking in a dramatic or exaggerated way. In science, the word has a quieter meaning. It refers to conditions that lie far outside the range we're familiar with. Places where temperature, pressure, gravity, or chemistry reach levels that challenge our assumptions about how planets behave. And once you begin looking for such conditions, it becomes clear that the universe has a remarkable talent for producing them. It helps, at first, to consider what we instinctively think of as normal. For most of us, the idea of a planet is shaped by the few we know well. Earth, of course, with its moderate temperatures and oceans. Mars, cold and dusty but still recognisable as a landscape. Jupiter, enormous and stormy, yet governed by physical laws we can understand without too much strain on the imagination. Even Venus, with its crushing atmosphere and searing heat, still feels like part of a familiar family. But the more planets astronomers have discovered around other stars, the more that sense of normality has faded. Our solar system, it turns out, may not be typical at all. Many planetary systems are arranged in ways that would seem chaotic if we tried to map them onto our own. Giant planets orbit where small rocky ones might be expected. Orbits are tilted or stretched into elongated shapes. Some planets circle their stars in just a few hours, while others take thousands of years to complete a single orbit. So what exactly makes a planet extreme? There isn't a single definition. Instead, astronomers think in terms of boundaries. A planet becomes extreme when one or more of its properties approaches the limits of what physics or chemistry can sustain. One of the most obvious of these properties is heat. Temperature on a planet depends largely on its distance from its star, but that's only part of the story. The composition of the atmosphere, the reflectivity of the surface, and the circulation of heat all play important roles. Even so, some planets orbit so close to their stars that the amount of energy they receive is staggering. To get a sense of this, imagine standing on Mercury, the innermost planet of our solar system. At noon, near the equator, temperatures can reach around 430 degrees Celsius. That is hot enough to melt lead. Yet Mercury is not considered especially extreme by exoplanet standards. There are planets where temperatures climb to more than 2,000 or even 3,000 degrees Celsius, hot enough to vaporize rock itself. On such worlds, the distinction between solid and gas begins to blur. Minerals that form mountains on Earth would exist as glowing vapor in the atmosphere. Winds could carry droplets of molten rock across the sky, condensing and falling like rain in places where temperatures briefly dip. It is difficult to picture, because our everyday experience gives us no reference point for landscapes made of liquid stone or clouds of iron vapor, and yet, according to our best measurements and models, such conditions are not only possible, they are real. Heat is only one dimension of extremity. Gravity is another. The strength of gravity on a planet depends on its mass and size. A planet much more massive than Earth can exert a surface gravity 2, 3, or even 10 times stronger than what we feel here. If you were somehow able to stand on such a world, every movement would feel heavier. Lifting your arm would require more effort. Walking would be slow and exhausting. Even breathing might feel different, as your chest worked harder against the weight of your own body. There are planets known as super-Earths, rocky worlds larger than our own, where gravity may be several times stronger than Earth's. These planets are not necessarily hostile in every way, but their environments would be profoundly unfamiliar to us. Mountains might not rise as high, because rock under strong gravity tends to collapse under its own weight. Atmospheres could be denser, pressed closer to the surface. At the opposite end of the spectrum are planets with very low densities, sometimes called puffed-up planets. These worlds can be enormous in size yet surprisingly light, composed largely of hydrogen and helium heated until they expand. Their gravity at the outer layers may be relatively gentle, even though their total mass is immense. Another way a planet can become extreme is through its orbit. In our solar system, most planets travel in nearly circular paths around the Sun, maintaining fairly stable distances. But some exoplanets follow highly elliptical orbits, swinging close to their stars and then drifting far away again. During the closest approach, temperatures may soar, while at the farthest point the planet cools dramatically. Such worlds experience seasons far more intense than anything on Earth, though calling them seasons hardly captures the scale of change. There are also planets that are tidally locked, meaning one side always faces the star while the other remains in perpetual darkness. On these worlds, the contrast between day and night can be extreme. The day side may be blisteringly hot, while the night side is cold enough for gases to freeze out of the atmosphere. Between them lies a narrow twilight region, where conditions might be less severe, a thin band encircling the planet like a permanent sunset. Wind, too, can reach extraordinary speeds under such conditions. When heat differences between day and night become large enough, the atmosphere begins to move in powerful currents, redistributing energy around the planet. Some exoplanets have winds measured at several kilometers per second, faster than the speed of sound in air. These are not gentle breezes, but vast, roaring flows of gas sweeping across entire hemispheres. Pressure is another factor that can push a planet into the realm of the extreme. Deep within gas giants, pressures climb to millions of times the atmospheric pressure at Earth's surface. Under such conditions, hydrogen itself may behave in unfamiliar ways, becoming metallic and conducting electricity. These exotic states of matter are difficult to reproduce even in laboratories on Earth, yet they may exist naturally inside many large planets. Chemistry, too, can take surprising forms. Atmospheres rich in carbon, sulfur, or other elements can produce clouds and weather unlike anything we see here. On some planets, temperatures and pressures allow compounds to form that would be unstable on Earth's surface. The sky itself could have colours and patterns that feel alien to human eyes. And then there is radiation. A planet orbiting very close to an active star may be bombarded by intense ultraviolet or X-ray radiation. This energy can heat the upper atmosphere until it begins to escape into space, forming vast tails of gas streaming away from the planet. Over time, such processes can strip a planet of much of its atmosphere, leaving behind a smaller, denser core. These are the kinds of conditions astronomers have in mind when they speak of extreme worlds. Heat intense enough to melt rock, gravity strong enough to reshape landscapes, winds faster than sound, radiation powerful enough to erode entire atmospheres. But there is another sense in which these planets are extreme, and it has less to do with numbers and more to do with possibility. Each discovery forces scientists to refine their understanding of how planets form and evolve. Every time a world is found that does not fit existing models, those models must be adjusted or expanded. In this way, extreme planets act almost like experiments conducted by nature itself. They show us what happens when initial conditions vary, when orbits shift, when stars behave differently, when chemistry unfolds under unfamiliar circumstances, they broaden the range of what we consider possible. It is also worth remembering that extreme does not necessarily mean permanent. Planetary systems change over time. Orbits can migrate. Atmospheres can be lost or gained. Temperatures can rise or fall as stars age. A planet that seems extreme today may not have been so in the past, and may not remain so in the distant future. Thinking about this can be strangely calming. The universe is not static. It is a place of gradual change, of processes unfolding over immense spans of time. Even the most hostile worlds are part of that slow evolution. As astronomers continued to discover more exoplanets, they began to notice patterns among the most extreme ones. Some of the hottest worlds, for example, belong to a class now known as hot Jupiters, giant planets orbiting extraordinarily close to their stars. Others were rocky worlds so heated that their surfaces appeared to be oceans of molten lava. Among the many kinds of extreme planets astronomers have identified, few capture the imagination as immediately as the so-called lava worlds. These are places where the surface is not made of solid ground in the way we understand it, but of molten rock, glowing and slowly shifting under temperatures so high that familiar minerals behave more like thick liquids than stone. It helps, at first, to picture how such a world comes to exist. Most lava planets are rocky bodies that orbit very close to their stars, often closer than Mercury orbits the Sun. At such distances, the energy pouring down from the star is immense. There is little chance for the surface to cool, and over time the upper layers of rock can begin to melt. Not just in isolated volcanic regions, as on Earth, but across entire hemispheres. One of the first planets of this kind to be studied in detail is known as Corot 7b. Discovered in 2009, it orbits its star in less than a single Earth day. That means its year, the time it takes to complete one orbit, is shorter than the time it takes us to sleep, wake, and go about an ordinary morning. At such proximity, the day side of the planet is heated to temperatures estimated to exceed 2000 degrees Celsius. At those temperatures, rock does not merely soften, it melts completely, forming vast seas of molten material. Scientists believe that on Corot 7b there may be enormous lava oceans stretching across the hemisphere that faces the star, their surfaces slowly churning in a thick glowing state. What makes this even more striking is that many of these planets are tidally locked. Just as the Moon always shows the same face to Earth, these worlds keep one side permanently facing their star. That means there is a day side where the heat is relentless, and a night side that never sees daylight at all. On the night side, temperatures can drop dramatically. In some cases, they may fall low enough for rock vapor carried from the hot hemisphere to condense and solidify. In a sense, these planets may experience something like a rock cycle driven not by water, but by evaporation and condensation of minerals. Vaporized stone rises on the day side, drifts through the atmosphere, and settles again in cooler regions. It is a strange idea, rock behaving almost like water on Earth, evaporating, forming clouds and falling again, and yet the physics supports it. At sufficiently high temperatures, even materials we think of as permanent and solid can become gases. Another example is Kepler 10b, one of the earliest rocky exoplanets confirmed by the Kepler mission. This world orbits so close to its star that its surface temperature is thought to be similar to that of molten lava. Its year lasts less than one Earth day, and its density suggests a composition rich in heavy elements, perhaps with a large iron core. When astronomers study such planets, they are not seeing detailed images of their surfaces. The distances are too great for that. Instead, they infer conditions from measurements of brightness, orbital behavior, and thermal emission. By analyzing the way the planet's light changes as it orbits, scientists can estimate how heat is distributed across its surface. In some cases, they can even detect differences between the day and night sides, observing how much infrared radiation is emitted. These measurements allow them to build models of what the surface and atmosphere might be like, and those models often point to landscapes dominated by molten rock. Another lava world that has drawn attention is 55 Cancri E, a planet roughly twice the size of Earth, but far denser than most planets of comparable radius. It orbits its star in just 18 hours. Observations suggest that its surface temperature may vary significantly, perhaps because lava flows and solidifies in different regions, altering how heat is radiated into space. There was once speculation that 55 Cancri might be rich in carbon, perhaps even containing large amounts of diamond deep within its interior. That idea has since been reconsidered as new data emerged, but it illustrates something important about the study of exoplanets. Our understanding evolves as better measurements become available. Early interpretations are refined, sometimes replaced entirely, as the picture grows clearer. Still, even without diamonds, a planet with global lava flows and extreme heat is remarkable enough. One of the more intriguing aspects of lava worlds is the possibility of lava weather. On Earth, weather is driven largely by water evaporating, condensing, and falling as rain. On a lava planet, similar processes could occur with silicate vapors. Winds might carry vaporized rock across the planet, where it cools and falls as droplets or particles. Imagine standing, if it were somehow possible, on the boundary between the hot and cooler regions of such a world. The sky might appear hazy with mineral vapor. The ground underfoot might glow faintly, not from reflected sunlight but from its own heat. Rivers, if they could be called that, would not be water but slow streams of molten stone, moving gradually under gravity. Of course, no human could survive such conditions, and even spacecraft would face severe challenges operating in such an environment. But through remote observation, we can still learn a surprising amount. There is also another mechanism that can create lava worlds, one that does not depend solely on proximity to a star. Tidal heating can play a role. In our own solar system, the moon Io, orbiting Jupiter, is the most volcanically active body known. Its interior is heated by the gravitational tug-of-war between Jupiter and neighbouring moons, which flexes and compresses it repeatedly, generating heat. Some exoplanets may experience similar or even stronger tidal forces, especially if their orbits are slightly elliptical. As they move closer to and farther from their stars, gravitational stresses can heat their interiors, driving intense volcanic activity that resurfaces the planet repeatedly. This means that not all lava worlds are simply baked by their stars. Some are heated from within, their interiors churning with energy released by gravitational interactions. Thinking about these processes can give a sense of how dynamic planets can be. It is easy to imagine planets as static objects, unchanging spheres drifting through space. But in reality, many of them are active, evolving, reshaped over time by heat, impacts, and internal motion. Another feature of lava planets that interests scientists is atmospheric loss. When a rocky planet orbits very close to its star, the intense radiation can strip away lighter elements from its atmosphere. In some cases, what remains may be a thin envelope of heavier gases and vaporized rock. Observations of certain exoplanets have revealed extended tails of material trailing behind them, somewhat like the tail of a comet. These tails are composed of gas and dust escaping the planet under the influence of stellar radiation and wind. Over long periods, this process can gradually erode a planet, reducing its mass. It is a reminder that planets are not always permanent in the forms we see them today. They can lose material, migrate in their orbits, or even be torn apart under extreme conditions. There is also something quietly fascinating about the timescales involved. A lava ocean on a distant planet may persist for millions or billions of years, far longer than any geological process on Earth has remained unchanged. From a human perspective, such worlds seem eternal, yet in the broader history of a planetary system, they may represent only one phase in a long evolution. As telescopes improve, astronomers are beginning to study lava planets in greater detail. instruments capable of analysing the light from these worlds are revealing clues about their composition and temperature. Some observations even hint at surface changes over time, suggesting that lava flows may shift and reshape the landscape. This level of detail, extracted from points of light many light years away, is a testament to the precision of modern astronomy. It also deepens our appreciation for how varied planetary environments can be. Another interesting question is whether lava worlds might once have been more temperate. A planet that migrates inward over time could have experienced cooler conditions earlier in its history. If so, its present state might be only the final stage of a long transformation. The surface gradually heated and melted as the orbit changed. Such possibilities remind us that planetary systems are not static. They evolve, sometimes dramatically, as gravitational interactions shift the positions of planets over millions of years. Not all extreme heat in the universe is found on rocky worlds with glowing surfaces. Some of the most astonishing temperatures ever measured belong to planets that are not solid at all, but enormous spheres of gas, worlds many times the mass of Earth, yet orbiting so close to their stars that their outer layers are heated to levels once thought impossible for a planet to endure. These are known as ultra-hot Jupiters, and the name itself hints at how unusual they are. The Jupiter in our own solar system is a cold giant, drifting far from the sun in a region where sunlight is faint, and temperatures in the cloud tops fall to around minus 145 degrees Celsius. It is a world of storms and thick atmospheres, but it is also a world of cold, a distant and dimly lit place. Now imagine taking a planet similar in size or even larger than Jupiter and moving it inward, closer and closer to its star, until its year lasts only a few days, or even just a single day. At that distance, the amount of energy pouring onto the planet becomes immense. The atmosphere heats, expands, and begins to behave in ways that challenge our understanding of weather and chemistry. One of the first surprises astronomers encountered when studying these planets was just how common they appeared to be among early discoveries. Hot Jupiters, and later the even more extreme ultra-hot Jupiters, were easier to detect than smaller planets, because their large masses caused noticeable wobbles in their stars, and their frequent transits produced clear signals in brightness measurements. For a time, it almost seemed as if such planets might dominate planetary systems, though later surveys revealed a much wider diversity of worlds. Still, the ones that orbit closest to their stars remain among the most dramatic. Take a planet like WASP-12b, for example. This world orbits so close to its star that it completes a full orbit in just over one Earth day. Its temperature is estimated to exceed 2,500 degrees Celsius, hot enough not only to melt metals but to break apart many molecules entirely. Under such conditions, the atmosphere is not a calm, layered structure like Jupiter's. It becomes a turbulent, glowing envelope of gas, heated and stirred by intense radiation. Astronomers studying WASP-12b have found evidence that the planet is actually being stretched by its star's gravity. The tidal forces are so strong that the planet is no longer perfectly spherical. Instead, it is slightly elongated, pulled into an oval shape, with its outer layers gradually escaping into space. In a sense, this planet is slowly evaporating. Streams of gas are being stripped away, forming a vast cloud around the star. Over long periods, such processes can significantly reduce a planet's mass, leaving behind a smaller remnant or, in some cases, perhaps nothing at all. It is a quiet kind of destruction, unfolding over millions of years, far too slowly to notice in a human lifetime, yet relentless in its progress. Another remarkable feature of ultra-hot Jupiters is the chemistry of their atmospheres. At the temperatures present on these worlds, substances that would normally condense into clouds or liquids remain in gaseous form. Iron, for example, which on Earth forms the solid metal in bridges and tools, can exist as vapour in the upper atmospheres of some of these planets. Observations of planets such as Kelt 9b, one of the hottest known, suggest temperatures so high that molecules are torn apart into their constituent atoms. The atmosphere becomes a place where hydrogen, oxygen, and metals exist in a kind of glowing, dissociated state, more like the outer layers of a star than anything we associate with a planet. Kelt 9b orbits a very hot star and receives enormous amounts of radiation. Its dayside temperature is estimated to exceed 4,000 degrees Celsius, hotter than the surface of some stars classified as red dwarfs. Under such conditions, the boundary between planet and star begins to feel less distinct. It is still a planet by definition, bound in orbit and lacking the mass to sustain nuclear fusion, yet its environment resembles stellar conditions in miniature. Winds on ultra-hot Jupiters are also extraordinary. Because many of these planets are tidally locked, one side always faces the star while the other remains in darkness. The temperature difference between the two hemispheres can be immense, and the atmosphere responds by circulating heat in powerful currents. Computer models and observations suggest that winds on some of these planets may reach several kilometers per second, far exceeding the speed of sound in their atmospheres. These winds transport heat from the day side toward the night side, preventing the temperature contrast from becoming even more extreme, though the difference is still dramatic. Imagine an atmosphere where entire jet streams span the globe, roaring continuously, carrying superheated gas from one hemisphere to another. There are no gentle breezes, no calm skies, only a perpetual flow driven by the energy of a nearby star. Clouds, if they form at all, are not made of water droplets or ice crystals. Instead, they may consist of exotic materials such as silicates or metal oxides, condensing at high altitudes where temperatures are slightly lower. In some cases, astronomers believe that molten droplets of iron may condense in cooler regions and fall as rain, only to evaporate again as they descend into hotter layers. It is a strange form of weather, one that stretches the meaning of the word, yet the underlying principles are the same as those shaping clouds and storms on Earth. Heat rises, gases circulate, materials condense and evaporate. The processes are familiar, but the scale and substances involved are profoundly different. Another curiosity of ultra-hot Jupiters is how inflated many of them appear to be. Some have radii significantly larger than Jupiter's, despite having similar or even smaller masses. The intense heating from their stars causes their atmospheres to expand, puffing them up like enormous balloons. This inflation reduces their density, making them some of the least dense planets known. There are worlds so large and diffuse that, if they could be placed in a vast enough ocean, they would theoretically float. Of course, such an ocean does not exist, but the comparison helps convey just how light these planets can be relative to their size. Astronomers are still studying the precise mechanisms behind this inflation. Heating alone may not fully explain it. Internal processes, magnetic interactions, and the absorption of stellar radiation at different depths in the atmosphere may all contribute. It is a reminder that even after decades of observation, these planets continue to pose puzzles. There is also the matter of formation. How do giant planets end up so close to their stars in the first place? According to most theories, gas giants form in the colder outer regions of a planetary system, where ices and gases are abundant. For a Jupiter-sized planet to orbit extremely close to a star, it likely formed farther out and migrated inward over time. This migration could occur through interactions with the protoplanetary disk of gas and dust from which the system formed, or through gravitational encounters with other planets. Over millions of years, the orbit gradually shrinks, bringing the giant planet closer and closer to its star until it reaches the scorching distances we observe today. Thinking about this process can give a sense of how dynamic planetary systems are. Orbits are not fixed forever. Worlds move, sometimes slowly, sometimes dramatically, reshaping the architecture of their systems as they go. There is something quietly humbling in that realization. Our own solar system, with its relatively stable and widely spaced planets, may be just one possible arrangement among many. Elsewhere, giant planets may have swept inward, scattering smaller worlds or altering their paths. Entire histories of planetary systems may have unfolded very differently from our own. Observing ultra-hot Jupiters has also taught astronomers a great deal about atmospheric physics under extreme conditions. By studying how these planets absorb and emit light, scientists can determine the presence of specific elements and measure temperature structures in the atmosphere. One technique involves observing the planet as it passes behind its star, an event called a secondary eclipse. During this brief period, the planet's light is blocked, allowing astronomers to measure the combined light of the star and planet before and after the eclipse, and isolate the planet's contribution. From this, they can estimate the temperature and composition of the dayside atmosphere. These measurements, carried out with space telescopes, have revealed atmospheres containing water vapour, carbon monoxide, sodium, and other elements, sometimes in unexpected proportions. Each observation adds another piece to the puzzle of how these planets function. There is also a quieter, almost philosophical aspect to studying such worlds. Ultra-hot Jupiters challenge our sense of what a planet is supposed to be. They are not places where life as we know it could exist, nor are they stable, temperate environments. They are dynamic, violent, and often short-lived on cosmic timescales, yet they are planets nonetheless, shaped by gravity, orbiting their stars, part of the vast diversity of worlds that populate the galaxy. And despite their harshness, there is something mesmerizing about imagining them. A giant sphere of glowing gas, tides stretching its shape, winds racing across its atmosphere, clouds of vaporized metal forming and dissolving in a continuous cycle, all under the unrelenting blaze of a nearby star. As telescopes become more sensitive, astronomers are beginning to detect smaller and more varied planets in similar orbits, some of them rocky, others intermediate in size between Earth and Neptune. Each new discovery expands our understanding of how close a planet can orbit and still survive, how atmospheres behave under extreme radiation, and how planetary systems evolve over time. Some planets do not experience sunrise and sunset the way Earth does. Instead, they show the same face to their star at all times, locked in a permanent orientation so that one hemisphere lives in unending daylight, while the other remains in darkness that never lifts. These are tidally locked worlds, and among the many kinds of extreme planets astronomers have discovered, they are some of the most intriguing to imagine. The reason this happens is actually familiar, though we rarely think about it. Our own moon is tidally locked to Earth. It rotates once on its axis in exactly the same time it takes to orbit us, which is why we always see the same lunar face. Over long periods, gravitational forces act like a brake, gradually slowing a body's rotation until it settles into this stable configuration. The process is quiet and slow, unfolding over millions or billions of years, but once complete, the result is permanent day on one side and permanent night on the other. When this occurs with a planet orbiting very close to its star, the consequences can be dramatic. The side facing the star absorbs enormous amounts of energy, heating continuously with no nighttime cooling. The opposite hemisphere, turned away from the star forever, radiates heat into space and grows cold, sometimes extremely cold, depending on the thickness of the atmosphere and how efficiently heat can circulate. At first glance, it might seem that such a planet would simply split into two extremes, a blazing desert on one side and a frozen wasteland on the other, and in some cases that may indeed be close to the truth. But atmospheres are rarely so simple. Air moves, heat flows, winds arise, attempting to balance the difference. One of the most studied examples of this kind of world is WAS P43b, a gas giant orbiting its star in less than a day. Observations have shown that its dayside temperature exceeds 2000 degrees Celsius, while the night side is far cooler, though still extremely hot by Earth standards. The difference between the two hemispheres is maintained by powerful winds that carry heat around the planet, though not efficiently enough to equalize conditions completely. The idea of winds strong enough to redistribute heat across an entire planet may sound dramatic, but it follows naturally from physics. When one region is heated intensely and another is not, pressure differences form. Gas flows from high pressure to low pressure areas, and on a rotating planet those flows become organized into global circulation patterns. On Earth, such patterns give rise to trade winds and jet streams. On tidally locked exoplanets, the same principles operate, but on a far larger and more intense scale. Computer simulations of these worlds suggest that winds may form broad streams flowing from the day side toward the night side, carrying energy and redistributing it across the atmosphere. In some cases, the hottest point on the planet is not directly beneath the star but shifted slightly, carried along by these currents. It is a reminder that even under extreme conditions, atmospheres behave in ways that are governed by the same basic rules everywhere in the universe. There is also a region between day and night that draws particular interest. This is sometimes called the terminator zone, the narrow band where the star sits permanently on the horizon. In this region, temperatures may be less extreme than on either hemisphere. On certain rocky planets, scientists have speculated that such a zone might even offer conditions where liquid water could exist. Provided the atmosphere is thick enough and the temperature range suitable, it is an intriguing possibility. Imagine standing in a place where the star never rises or sets, where the sky holds a constant twilight glow, where one direction leads toward a hot, bright desert, and the other toward an endless frozen darkness. The winds might blow steadily from one side of the planet to the other, carrying heat and clouds along a continuous path. Of course, many tidally locked planets are far too hot or too cold for such temperate conditions to exist. Yet the idea illustrates something important. Extremes are not always uniform. Even on worlds that seem hostile at first glance, there can be gradients, transitions, and regions where the environment changes in unexpected ways. Another fascinating aspect of tidally locked planets is how their atmospheres respond over time. If the atmosphere is thin, heat may not circulate effectively, and the temperature contrast between day and night becomes severe. The night side could become so cold that gases begin to freeze out, forming frost or even solid deposits of atmospheric components. Over long periods, this process could deplete the atmosphere on the night side, locking gases into ice. If the atmosphere is thick, however, it can transport heat more efficiently, smoothing out temperature differences and preventing extreme freezing. This is one reason astronomers pay close attention to atmospheric composition and pressure when studying exoplanets. The thickness of the atmosphere can dramatically influence the climate of a world. Tidally locked planets are especially common around red dwarf stars, which are smaller and cooler than the Sun. Because these stars emit less energy, their habitable zones, the regions where temperatures might allow liquid water to exist, lie much closer to the star. Planets in these zones are likely to become tidally locked over time. The TRAPPIST-1 system is a well-known example. This star hosts several Earth-sized planets, many of which are believed to be tidally locked. Scientists are studying them carefully, trying to determine whether their atmospheres might be thick enough to transport heat and maintain stable climates. These studies are still ongoing, but they offer a glimpse into the diversity of planetary environments that may exist even among relatively small worlds. There is also a psychological aspect to imagining such planets. On Earth, our daily rhythms are shaped by the cycle of day and night. We wake, we work, we rest, all guided in part by the rising and setting of the sun. On a tidally locked world, that cycle would not exist. Time would still pass, of course, but the sky would not mark it in the same way. The star would remain fixed in the same place, and shadows would never move. It is difficult to picture how that might feel, to live in a place where the lighting never changes, where morning and evening are concepts without meaning. And yet, from a physical perspective, such conditions are entirely natural outcomes of gravitational forces acting over long spans of time. Observing these planets requires careful measurements. Astronomers often study how heat is distributed across the surface by measuring infrared radiation as the planet orbits its star. As different regions come into view, the amount of emitted heat changes slightly, allowing scientists to infer temperature patterns. These observations are subtle and require extremely sensitive instruments, but they provide valuable insights into atmospheric circulation and energy transport. Over time, they help build a clearer picture of how climates operate under conditions very different from those on Earth. Another curious effect on tidally locked planets involves clouds. On the day side, intense heating may cause strong upward convection, leading to the formation of thick cloud layers. These clouds can reflect some of the incoming starlight, reducing the amount of energy reaching the surface. On the night side, cooler temperatures may allow different types of clouds to form, perhaps composed of materials that would be unusual on Earth. The distribution of clouds can influence the planet's temperature and appearance, creating patterns that shift over time as atmospheric currents move them around. In some models, large, bright cloud formations may gather near the substellar point, the region directly facing the star, acting almost like a natural sunshade. Thinking about these processes helps illustrate how dynamic planetary climates can be, even under extreme and seemingly unchanging conditions. A world of eternal day is not static. Heat rises, winds flow, clouds form and dissipate, and the atmosphere remains in constant motion. There is also the question of geology. On rocky, tidally locked planets, the dayside heat could drive intense volcanic activity, particularly if the interior retains significant energy from formation or tidal heating. Lava flows might reshape the surface repeatedly, while the night side preserves older terrain in the deep cold. Over millions of years, such differences could produce hemispheres with very different landscapes, one constantly renewed, the other largely unchanged. As astronomers continue to study these worlds, they are refining models of how atmospheres behave, how heat is transported, and how different factors combine to shape planetary environments. Each new observation adds detail to a picture that is still being assembled. What emerges from these studies is a sense that planets are not simply categorized as hot or cold, habitable or inhospitable. They exist along a spectrum of conditions shaped by many interacting variables. Distance from the star, atmospheric composition, rotation rate, and internal heat all play roles, and small differences can lead to dramatically different outcomes. It is also worth remembering that tidally locked planets are not rare exceptions. In fact, they may be among the most common types of planets in the galaxy, particularly around the most numerous stars. This means that worlds of permanent day and night may outnumber those with familiar day-night cycles like our own. That thought can shift our perspective in a quiet way. The rhythm of sunrise and sunset, which feels so fundamental to life on Earth, may not be the default pattern for planets. It is simply one possibility among many. There are places in the universe where the atmosphere does not move in gentle currents or seasonal breezes, but in vast, relentless rivers of wind that race around an entire planet faster than the speed of sound. On these worlds, weather is not something that passes through in a few hours or days. It is constant, powerful and global, driven by differences in temperature so extreme that the air itself is forced into motion on a planetary scale. To understand how this happens, it helps to begin with something familiar. On Earth, wind forms because different parts of the planet are heated unevenly. The equator receives more sunlight than the poles, and the rotation of the planet shapes the movement of air into large circulation cells. These patterns create trade winds, jet streams and storms. Even hurricanes, powerful as they are still relatively small features compared with the size of the planet. Now imagine increasing the temperature difference by hundreds or even thousands of degrees. Imagine a planet where one hemisphere is heated relentlessly by a nearby star while the other remains much cooler. And imagine that this contrast never changes because the planet is tidally locked. Under such conditions, the atmosphere has no choice but to respond dramatically. Air expands on the hot side, rises and flows toward the cooler side in enormous streams. The result is a circulation pattern that can span the entire globe. Astronomers have measured wind speeds on some exoplanets that exceed several kilometers per second. That is many times faster than the strongest winds ever recorded on Earth. At those speeds, the movement of gas is not merely a breeze or even a storm. It becomes a roaring, continuous flow, a permanent jet stream encircling the planet. One of the best studied examples of such a world is HD 189733b, a hot Jupiter located about 64 light-years away. This planet has become famous not only for its violent winds, but also for what those winds carry. Observations of HD 189733b suggest that its atmosphere contains clouds of silicate particles, materials similar to the components of sand and glass on Earth. At the temperatures present in the upper atmosphere, these materials can condense into tiny grains suspended in the air. And when winds reach supersonic speeds, those grains are carried sideways through the atmosphere at extraordinary velocities. In a sense, this means that on HD 189733b, it may rain glass. Not in the way rain falls gently through air on Earth, but in sideways sheets driven by winds so strong that particles never fall straight down. Instead, they sweep across the planet in a constant abrasive storm. It is difficult to picture such a thing, because our experience of weather is shaped by the mild conditions of Earth's atmosphere. Even the harshest desert sandstorm is brief compared with the permanent global-scale storms of these distant worlds. On HD 189733b, the winds never truly stop. The temperature gradients that drive them are constant, and the planet's rapid orbit and rotation maintain the circulation. Another aspect of these extreme atmospheres is the way heat is transported. Supersonic winds do more than carry particles. They redistribute energy around the planet, preventing the day side from becoming even hotter and the night side from becoming even colder. In some cases, the hottest region of a planet is shifted away from the point directly facing the star, carried eastward by fast-moving winds. Astronomers can detect this effect by measuring infrared light emitted from different parts of the planet as it orbits. By analysing these variations, they can infer temperature maps, revealing how heat moves through the atmosphere. These maps are not detailed images in the way we might photograph Earth from space, but they provide enough information to show that entire atmospheres are in motion. Another remarkable example is WASP 76b, a planet that has drawn attention for a particularly striking phenomenon. Observations suggest that iron vapour exists in its atmosphere on the day side where temperatures are high enough to vaporise metal. Winds then carry this vapour toward the cooler night side, where it condenses and falls, possibly as droplets of molten iron. The idea of iron rain might sound like something from a science fiction novel, yet it follows naturally from the physics of high temperatures and atmospheric circulation. Materials that are solid on Earth become gases under extreme heat. When they move into cooler regions, they condense again, forming clouds and precipitation, just as water does here. What makes these processes especially fascinating is that they are governed by the same physical principles we see on Earth. Evaporation, condensation, pressure gradients, and wind formation are universal phenomena. The difference lies in scale and composition. Instead of water, there may be silicates or metals. Instead of gentle convection, there may be supersonic jet streams. The atmospheres of such planets are also shaped by intense radiation from their stars. High-energy ultraviolet light can break apart molecules, creating layers of ionized gas. Magnetic fields, if present, may interact with these charged particles, producing aurora-like phenomena far more powerful than those seen near Earth's poles. There is also the question of how such winds affect the structure of the atmosphere itself. At very high speeds, turbulence becomes significant. Shock waves may form, and layers of gas can mix in complex ways. These processes are difficult to model even with modern computers, and astronomers continue to refine their understanding as new observations become available. One of the challenges in studying these worlds is that the signals we detect are extremely faint. We cannot watch the winds directly or see the storms unfold. Instead, we observe changes in light, subtle variations in spectra, and shifts in brightness that hint at the processes occurring far away. It's a bit like trying to understand the weather in a distant city by watching the glow of its streetlights flicker through fog. Despite these limitations, the progress has been remarkable. Each year, new techniques allow astronomers to extract more information from the light of distant stars and planets. Instruments capable of analysing infrared wavelengths, in particular, have opened a window into atmospheric dynamics that was once completely inaccessible. Another interesting consequence of supersonic winds is the way they can shape the distribution of clouds. On some planets, clouds may form in bands or arcs, stretched by high-speed currents. The appearance of the planet, if it could be seen directly, might change over time as these patterns shift, much as Jupiter's cloud belts evolve, but on a far more extreme scale. There is also evidence that in some cases, the atmospheres of hot Jupiters are being gradually stripped away by stellar radiation and wind. Supersonic flows may help carry material to the upper atmosphere, where it can escape into space. Over millions or billions of years, this process could significantly alter a planet's mass and composition. Thinking about these worlds can give a new appreciation for how varied planetary environments can be. On Earth, weather is something we talk about casually, checking forecasts, noticing changes in temperature or rain. But in the broader universe, weather can take forms that are almost unimaginable, driven by energies and forces far beyond our everyday experience. It is also worth considering how these discoveries were made. The detection of supersonic winds and exotic precipitation did not come from direct observation in the way we might watch a storm on Earth. Instead, it emerged from careful analysis of spectral lines, measurements of heat distribution, and the application of physical models. The conclusions are grounded in evidence, yet they require a willingness to imagine conditions far removed from anything familiar. There is a quiet beauty in that process. Scientists begin with small clues, tiny shifts in light or temperature, and gradually build a picture of an entire world. Its atmosphere in motion, its clouds forming and dissolving, its winds racing endlessly around its circumference. And while these planets may seem violent and inhospitable, they are also part of the natural diversity of planetary systems. They remind us that the universe is not limited to gentle climates and stable conditions. It is capable of producing environments that push matter and energy to their limits, shaping worlds in ways that are both harsh and fascinating. Not all extreme planets are defined by blazing heat or violent winds. Some are remarkable for a very different reason. Instead of shining brightly in reflected starlight the way Jupiter or Venus might, they absorb almost everything that falls upon them. These worlds are so dark that, in visible light, they would appear as nearly perfect silhouettes, swallowing the glow of their stars rather than scattering it back into space. To understand why this is unusual, it helps to think about how planets normally appear. When we see a planet, whether through a telescope or in photographs taken by spacecraft, what we are really seeing is reflected light. Sunlight strikes clouds, ice, rock, or gas, and some portion of that light bounces back toward our eyes. The fraction that is reflected is called albedo. A high albedo means a bright world. A low albedo means a dark one. Earth, with its clouds and oceans, reflects roughly 30% of the sunlight that reaches it. Venus reflects even more, its thick cloud cover acting like a brilliant mirror, making it one of the brightest objects in our sky. Even the moon, which looks grey and subdued, reflects about 12% of the sunlight it receives, but there are planets whose atmospheres and surfaces reflect almost nothing at all. One of the most famous examples is a planet known as TREES 2b. This gas giant orbits its star at a relatively close distance, and has been studied carefully by astronomers because of its extraordinary darkness. Measurements suggest that it reflects less than 1% of the light that reaches it. To put that into perspective, this planet is darker than coal, darker than asphalt, darker even than many materials designed on Earth to absorb light. If you could somehow see TRES 2b up close in visible light, it would not resemble the banded, swirling appearance of Jupiter. Instead, it might look like a faintly glowing ember, illuminated only by the dim red heat of its own atmosphere rather than by reflected starlight. The reason for this darkness lies in the chemistry and structure of its atmosphere. Many bright planets owe their reflectivity to clouds, layers of condensed particles that scatter light in many directions. On Earth, water clouds perform this role. On Venus, thick sulfuric acid clouds do the same. But on a very hot planet, temperatures may be too high for reflective clouds to form. Instead, the atmosphere may contain gases that absorb light efficiently. Sodium, potassium, titanium oxide and other compounds can capture incoming radiation, converting it into heat rather than reflecting it. In such an atmosphere, starlight penetrates deeply, absorbed layer by layer, leaving little to escape back into space. The result is a world that appears almost black, even though it may be extremely hot. There is also another factor that contributes to this effect. At high temperatures, molecules that would normally form clouds can be broken apart or prevented from condensing. Without clouds to scatter light, the atmosphere becomes clearer but also darker, allowing radiation to pass inward and be absorbed. It is interesting to consider how different such a planet would look compared with the gas giants we know. Jupiter's bright bands and zones are visible because of complex cloud layers reflecting sunlight. Remove those clouds, and much of the visible brightness would vanish, leaving a much darker sphere. Astronomers have also discovered planets whose darkness may be enhanced by high-altitude hazes composed of complex hydrocarbons or other particles. These hazes can absorb light very effectively, producing a deep, muted appearance. Similar processes occur on Saturn's moon Titan, though on a smaller scale, where a thick orange haze dims and reddens the sunlight reaching the surface. On an exoplanet with stronger radiation and different atmospheric chemistry, such hazes could become even more effective at absorbing light, turning the planet into a nearly perfect absorber. What makes these dark worlds especially fascinating is that, despite their lack of reflected light, they can still be studied. Infrared observations reveal the heat they emit, allowing astronomers to measure their temperatures and learn about their atmospheres. In some cases, the contrast between visible darkness and strong infrared emission makes the planet easier to detect in thermal wavelengths than in reflected light. This dual nature, dark in visible light yet glowing in heat, gives these planets an unusual character. They are not invisible, but they are visible in a different way, revealing themselves through warmth rather than brightness. Another intriguing aspect of low albedo planets is how their darkness influences their climate. A world that absorbs most of the light it receives will heat more efficiently than one that reflects a large fraction of it. This can raise atmospheric temperatures and alter circulation patterns, potentially intensifying winds and chemical reactions. In this way, darkness is not merely an appearance. It becomes an active part of the planet's physical behavior, shaping its environment over time. There is also something quietly thought-provoking about the idea of a dark planet orbiting a bright star. From a distance, the star would shine brilliantly, yet the planet itself would be difficult to see, a faint silhouette crossing the stellar disk during a transit. It would be present, massive and real, yet visually subdued, revealing itself only through careful measurement. It reminds us that brightness is not always a measure of significance. Some of the most interesting objects in the universe are not the ones that shine the most brightly, but the ones that absorb, transform and quietly radiate energy in less obvious ways. As astronomers continue to refine their techniques, they are discovering more planets with unusually low albedos. Each one provides another opportunity to study atmospheric chemistry under extreme conditions. By comparing dark planets with brighter ones, scientists can learn how temperature, composition, and radiation interact to shape planetary climates. There is also the possibility that some rocky planets, not just gas giants, may have very low reflectivity. A surface composed of dark basaltic rock, for example, would absorb much of the incoming light. If such a planet lacked clouds or ice, its overall appearance could be very dim, even if it were otherwise similar in size to Earth. Imagining standing on such a world leads to an unusual picture. The sky might appear darker than expected, the star above blazing, yet the landscape around you absorbing much of the light, giving the ground a muted, shadowed quality. Colours might appear subdued, contrasts softened by the lack of reflection. And yet, even such a world would not be completely without beauty. The glow of the star, the faint shimmer of heated air, perhaps the distant sight of another planet or moon in the sky, all would still be there, shaped by the same physical laws that govern every corner of the universe. These dark planets also remind us that extreme conditions do not always mean violent or chaotic ones. Sometimes extremity takes the form of quiet absorption, of light disappearing rather than scattering, of heat building gradually in an atmosphere that holds onto every photon it receives. It is another example of how varied planetary environments can be, and how many different paths nature can take when shaping worlds. Some planets may be dominated not by rock, not by storms of silicate or metal, and not by vast, scorching deserts of molten stone, but by something far more familiar to us, at least in principle: water. Yet the familiarity fades quickly when the scale becomes clear, because these worlds are not like Earth, where oceans cover part of the surface and continents rise above the waves. Instead, these are planets where water may extend uninterrupted across the entire globe, forming oceans hundreds of kilometers deep with no shorelines, no mountains breaking the surface, and no dry land at all. It is a quiet but powerful idea, a world with no beaches, no cliffs, no continents, just a horizon of water in every direction, stretching endlessly under the sky. And while it might sound like a setting imagined for fiction, astronomers have good reasons to believe such planets exist in large numbers. To understand how a planet can become a water world, it helps to look back at how planets form in the first place. In the early stages of a planetary system, a disk of gas and dust surrounds a young star. Within this disk, particles collide and gradually build up into larger bodies, eventually forming planets. The composition of these planets depends strongly on where they form. Close to the star, temperatures are high, and volatile substances like water tend to evaporate, leaving behind rock and metal. Farther out, where it is colder, ices can condense, allowing planets to accumulate large amounts of water and other frozen compounds. Some of these icy bodies may migrate inward over time, moving closer to the star. If conditions are right, the ice melts, forming deep global oceans. Because these planets began with far more water than Earth ever had, their oceans can become extraordinarily deep, far deeper than the Mariana Trench, which reaches about 11 kilometers below sea level. On a true water world, the ocean might extend hundreds of kilometers downward, before reaching the underlying layers of high-pressure ice or rock. The idea of high-pressure ice is an interesting one. On Earth, ice forms at low temperatures, floating on water because it is less dense. But under extreme pressure, water can freeze into forms that are denser than liquid water, sinking rather than floating. These exotic forms of ice are unfamiliar in everyday life, but they have been created in laboratories and are thought to exist naturally deep within icy moons like Europa and Ganymede. On a large water world, the pressure at great depths could be so high that layers of such ice form at the bottom of the ocean, separating the liquid water above from the rocky mantle below. This would create an environment very different from Earth's oceans, where water interacts directly with the seafloor, exchanging minerals and heat. Without that interaction, the chemistry of the ocean might evolve in very different ways. One of the most intriguing examples of a possible water world is a planet known as Kepler-22b. This planet lies in the habitable zone of its star, the region where temperatures might allow liquid water to exist. It is larger than Earth, and its density suggests that it could contain a significant amount of water, though its exact composition remains uncertain. Another candidate is GJ1214b, a planet often described as a mini Neptune or water-rich world. Observations indicate that it has a thick atmosphere and may contain a large fraction of water beneath that atmosphere, though the details are still being studied. The light passing through its atmosphere suggests the presence of clouds or hazes, which make it difficult to see deeper layers, but models indicate that vast oceans could exist below. Thinking about such planets invites a shift in perspective. On Earth, water is something we encounter in lakes, rivers and seas, bounded by land and shaped by coastlines. On a water world, the ocean itself defines the planet. Weather, climate, and even the colour of the sky would be influenced by the immense presence of water. Cloud formation, for example, might be more extensive, with large portions of the planet covered by thick cloud layers reflecting sunlight. Storm systems could grow larger and last longer, drawing energy from the warm ocean below. Waves might travel unimpeded around entire hemispheres, building into long rolling swells that circle the planet. It is also possible that some water worlds experience cycles of evaporation and condensation on a scale far greater than anything on Earth. The atmosphere above a warm global ocean could become rich in water vapour, creating a powerful greenhouse effect that traps heat and stabilises temperatures. There is another aspect of these planets that captures the attention of scientists, and that is the question of life. Water is often considered a key ingredient for life as we know it, and the presence of vast oceans naturally raises the possibility that biological processes could occur there. However, the absence of continents and shallow coastal regions might limit the availability of certain nutrients, and the presence of high-pressure ice layers could isolate the ocean from the planet's interior. This does not rule out life, but it suggests that any ecosystems might be quite different from those on Earth. Perhaps life, if it exists, would rely on chemical gradients within the ocean itself, rather than on interactions with a rocky seafloor. Another fascinating possibility involves temperature gradients in the ocean. On Earth, sunlight warms the upper layers of the sea, while deeper layers remain cold. On a water world, similar stratification could occur with layers of differing temperature and composition. Currents might circulate slowly, driven by differences in density, distributing heat and nutrients through the vast depths. The scale of such oceans is difficult to grasp. The deepest parts of Earth's oceans already seem immense to us, yet they would be shallow compared with what might exist on some of these planets. Pressure increases steadily with depth, and at great depths, the environment would be one of crushing weight and darkness, far beyond what any human-made vessel could easily explore. Despite these challenges, astronomers are learning to study water-rich planets in surprising ways. By measuring the mass and radius of a planet, they can estimate its average density. A density lower than that of rock, but higher than that of gas, suggests the presence of significant amounts of water or ice. Spectroscopy can also reveal the presence of water vapour in an atmosphere, providing further clues. In recent years, space telescopes have begun to detect signs of water in the atmospheres of some exoplanets, though determining whether that water exists as vapour, liquid, or ice requires careful analysis. Each new observation adds another piece to the puzzle, gradually refining our understanding of these distant oceans. It is also worth considering how different the sky might appear from the surface of such a world. With no land to break the horizon, the view would be dominated by water and sky alone. If the atmosphere were thick and cloud-rich, the sunlight might appear diffused, creating a soft, even illumination. At night, if the planet had a moon, its reflection might stretch across the ocean in a continuous path of light, unbroken by shoreline or terrain. And yet, despite their vast oceans, water worlds are not necessarily calm or peaceful places. Strong winds could drive enormous waves, and storms could grow to sizes rarely seen on Earth. Lightning might flash across wide expanses of cloud, illuminating the sea below. The atmosphere interacting with the ocean would be in constant motion. There is also the possibility of tidal forces shaping the oceans. If a water world orbits close to its star or has a large moon, tides could rise and fall dramatically. Though without continents to channel them, the patterns might be more uniform, sweeping across the globe in slow, powerful surges. As we learn more about these planets, it becomes clear that they occupy an important place in the spectrum of planetary types. They are not gas giants, not rocky deserts, but something in between, worlds where water dominates, but conditions may vary widely depending on temperature, atmosphere, and orbital distance. And thinking about them also invites reflection on Earth itself, our planet's balance of land and water, its moderate oceans and diverse environments, may not be the most common arrangement in the universe. There may be far more planets covered entirely by water, or entirely by rock, or entirely by ice, than planets with the particular combination we know. Each discovery broadens our sense of what a planet can be, reminding us that the familiar is only one possibility among many. There are planets that never see a sunrise, not because they are tidally locked or buried beneath clouds, but because they have no star at all. These worlds travel alone through the galaxy, drifting in darkness, untethered to any sun, carrying with them only the faint warmth left over from their formation and whatever heat their interiors still generate. They are known as rogue planets, and among all the extreme worlds astronomers have discovered, they may be the most solitary. The idea of a planet wandering through interstellar space once sounded improbable, almost poetic rather than scientific. For a long time, planets were assumed to form within stable systems and remain there, orbiting their stars for billions of years. But as astronomers began studying the dynamics of planetary systems more closely, it became clear that gravity does not always produce quiet, orderly arrangements. It can also create chaos, scattering worlds outward like stones flung from a spinning wheel. In the early stages of a planetary system, newly formed planets interact strongly with one another. Their orbits may shift as they exchange gravitational pulls, and sometimes those interactions grow violent. A close encounter between two massive planets can send one of them spiraling inward toward the star, while the other is flung outward at high speed. If the outward motion is strong enough, the planet escapes the star's gravity entirely and begins a long, solitary journey through the galaxy. This process, known as gravitational ejection, is now believed to be common. Computer simulations of planetary formation show that many systems may eject one or more planets during their early history. Some estimates suggest that rogue planets could be nearly as numerous as stars in the Milky Way. That means there may be billions, perhaps even hundreds of billions, of these wandering worlds drifting silently in the dark. Detecting them is not easy. Without a nearby star to illuminate them, rogue planets emit very little visible light. Most of what we can detect comes from their residual heat, the faint infrared glow that lingers from the time they formed. Young rogue planets, still warm from their birth, are easier to find because they radiate more strongly in infrared wavelengths. Astronomers also use a technique called gravitational microlensing to detect these worlds. When a rogue planet passes in front of a distant star, its gravity bends and magnifies the star's light for a brief period. The brightening may last only hours or days, but careful measurements can reveal the presence of a massive object, even if it is completely dark. One of the most intriguing discoveries in recent years has been the identification of groups of free-floating planetary mass objects in star-forming regions. Some of these objects are only a few times the mass of Jupiter, yet they are not bound to any star. They appear to have formed in much the same way as planets, but were either ejected early or never captured by a stellar system at all. Thinking about such a world can be strangely calming. Imagine standing, if it were somehow possible, on the surface of a rogue planet. There would be no sunrise, no bright disk climbing above the horizon. The sky would remain permanently dark, filled with distant stars, perhaps brighter and clearer than we ever see from Earth, because there would be no atmosphere scattering light from a nearby sun. The ground beneath your feet would depend on the planet's composition. Some rogue planets may be gas giants, vast spheres of hydrogen and helium with no solid surface at all. Others could be rocky worlds, frozen solid, their oceans locked beneath layers of ice. A few might even retain thick atmospheres that trap heat, allowing subsurface oceans to remain liquid despite the absence of sunlight. This last possibility has drawn particular interest from scientists. On Earth, we often think of sunlight as the primary source of energy for life. Yet there are ecosystems deep in the ocean, near hydrothermal vents, that rely entirely on chemical energy from the planet's interior. If a rogue planet had sufficient internal heat and a thick insulating layer of ice or atmosphere, it might maintain pockets of liquid water for millions or billions of years. In such an environment, any life that arose would live in darkness, guided not by sunlight but by chemistry and heat. It would be a very different kind of biosphere, if it existed at all, but the possibility reminds us that life, like planets, may find ways to persist in unexpected places. Another fascinating aspect of rogue planets is their temperature. Without stellar radiation, their surfaces would be extremely cold, often just a few tens of degrees above absolute zero. The atmosphere, if present, could freeze out and fall as snow, forming layers of nitrogen, methane or other compounds on the ground. Yet deep below the surface, temperatures might be warmer. Radioactive decay within the planet's interior produces heat, and in large planets this heat can remain trapped for long periods. On gas giants, the interior can remain relatively warm for billions of years, slowly radiating energy into space. There is also the possibility that some rogue planets are not entirely alone. A planet ejected from a system might carry moons with it, bound by its gravity even as it drifts through interstellar space. In such a system, the primary source of illumination could be the faint glow of the planet itself, reflected from the icy surfaces of its moons. The thought of a small moon orbiting a dim glowing planet in the vast darkness between stars is a quiet and haunting one. There would be no seasons, no changing constellations due to a nearby sun, only the slow motion of distant galaxies and the steady orbit of the moon overhead. Astronomers have also considered the possibility of rogue planets passing near other stars over long timescales. The galaxy is vast, and the distances between stars are immense, but over millions or billions of years close encounters can occur. A rogue planet might pass through the outer regions of another star system, briefly warmed by its light before continuing on its journey. In rare cases, it is even possible that a rogue planet could be captured by another star's gravity, becoming part of a new planetary system. Such events are thought to be uncommon, but they illustrate how dynamic the galaxy can be over long periods. There is something quietly profound about the existence of rogue planets. They remind us that not all worlds belong to orderly systems with predictable orbits and regular days. Some are wanderers, shaped by chance encounters and gravitational forces, travelling alone through the darkness for billions of years. It also changes how we think about the galaxy itself. The space between stars is not empty. It may be populated by countless unseen planets, drifting silently, each with its own history, its own composition, its own long journey through the interstellar night. Observing these worlds requires patience and ingenuity. Infrared telescopes, sensitive detectors, and long-term surveys are gradually revealing more of them. Each discovery adds to the growing realization that planets are not confined to the neighborhoods of stars, but are scattered throughout the galaxy in ways we are only beginning to understand. And while rogue planets may seem lonely from our perspective, they are part of the same cosmic processes that formed every other world. They were born in disks of gas and dust, shaped by gravity, heated by collisions and radioactive decay. Their paths diverged, but their origins are shared with planets like Earth. Thinking about that can bring a sense of connection rather than isolation. Even a world drifting alone between stars is still part of the galaxy, still bound by the same physical laws, still carrying the history of its formation within its rocks or clouds. If you were to look only at the planets in our own solar system, you might come away with the impression that planets fall neatly into a few categories. There are small rocky worlds like Mercury, Venus, Earth, and Mars. There are gas giants like Jupiter and Saturn. And there are the ice giants, Uranus and Neptune, occupying a kind of middle ground. For a long time, this seemed like a sensible way to think about planets, almost as if nature preferred these few familiar templates. But as astronomers began discovering planets around other stars, something unexpected appeared again and again. Worlds that did not fit neatly into any of those categories. Planets larger than Earth, but smaller than Neptune, composed of mixtures of rock, water, and gas in proportions we had never seen before. Others so massive that they approached the boundary between planets and brown dwarfs, objects too large to be ordinary planets, yet too small to ignite sustained nuclear fusion like stars. These worlds are often called super-Earths and megaplanets, and they remind us that the solar system, familiar as it feels, may not represent the most common arrangement of planets in the galaxy. Let's begin with super-Earths. Despite the name, a super-Earth is not necessarily Earth-like in any comforting sense. The term simply refers to a planet with a mass greater than Earth's, but significantly less than that of Uranus or Neptune. These planets may be rocky, water-rich, or enveloped in thick atmospheres. The name describes size, not environment. Some super-Earths are thought to be dense, with strong gravity and thick crusts. Imagine standing on such a world, if it were possible, and feeling your weight doubled or tripled compared with what you experience on Earth. Mountains might rise only modestly before collapsing under their own weight. The atmosphere, if present, could be compressed into a dense layer close to the surface, perhaps producing heavy clouds and persistent haze. One of the first super-Earths to capture widespread attention was Gliese 581c, discovered in 2007. At the time, it was considered a potential candidate for a habitable world, though later studies suggested it was likely far too hot. Even so, the discovery demonstrated that rocky planets larger than Earth were not only possible but relatively common. Since then, many more have been found. Kepler 10c, sometimes called a mega-Earth, is a striking example. This planet has a mass about 17 times that of Earth, yet it appears to be primarily rocky rather than gaseous. Before its discovery, many scientists believed that planets of such mass would inevitably accumulate thick envelopes of hydrogen and helium, becoming gas giants. Kepler 10c challenged that assumption, showing that massive rocky planets could exist under certain conditions. Thinking about a rocky planet with such mass invites interesting questions about its interior. The pressure deep inside would be immense, far greater than in Earth's core. Minerals would be compressed into dense, unfamiliar forms, and the boundary between mantle and core might behave differently than anything we know here. The gravity on the surface of such a world would also influence its atmosphere and weather. Winds might move differently in dense air. Clouds could form at lower altitudes. Rain, if it occurred, might fall more quickly under stronger gravity, shaping landscapes in ways that are difficult to picture without careful modelling. There are also planets known as mini-Neptunes, which occupy a size range between Earth and Neptune, but are composed largely of gas or volatile substances. These worlds may have deep atmospheres overlaying layers of water or exotic ices, with no solid surface in the sense we understand it. GJ1214b is a well-known example. Its density suggests that much of its interior may consist of water or other light materials, possibly in forms compressed by pressure into exotic states. Observations of its atmosphere reveal thick clouds or haze, making it difficult to see deeper layers, but its overall properties indicate a planet quite unlike any in our solar system. One of the reasons super-Earths and mini-Neptunes are so interesting to astronomers is that they appear to be among the most common types of planets in the galaxy. Surveys suggest that many stars host planets in this size range, even though our own solar system contains none. That absence is itself a puzzle. Why did our system produce small rocky planets and large gas giants but no intermediate worlds? The answer is still being studied. Moving to even larger scales, we encounter planets that stretch the definition of what a planet can be. Some are so massive that they approach the lower limit for brown dwarfs, objects sometimes described as failed stars. The dividing line between a very large planet and a brown dwarf is often placed around 13 times the mass of Jupiter, the point at which deuterium fusion can occur in the interior. Yet the boundary is not perfectly sharp, and there are objects whose classification depends as much on their formation history as on their mass. One example is a planet known as HD 100546b, an enormous world still forming within a disk of gas and dust around a young star. Observations suggest that it may be several times the mass of Jupiter and still accumulating material. Watching such a planet in the process of formation offers a rare glimpse into the early stages of planetary evolution. There are also planets with masses exceeding 10 times that of Jupiter, orbiting at distances where they remain relatively cool compared with the ultra-hot Jupiters we discussed earlier. These massive worlds have strong gravity and deep atmospheres, and their interiors may contain layers of metallic hydrogen under pressures far greater than those in Jupiter's core. The existence of such massive planets raises questions about how large a planet can become before it crosses the threshold into becoming a star. Nuclear fusion requires extremely high temperatures and pressures, and only objects above a certain mass can sustain it. Below that threshold, even the largest planets remain dark, radiating only the heat left over from their formation. Another fascinating aspect of super-Earths and megaplanets is how they influence their surroundings. A massive planet can shape the architecture of its entire planetary system, altering the orbits of smaller worlds or even ejecting them entirely. In some systems, giant planets appear to have migrated inward, disrupting the formation of smaller planets closer to the star. This process may explain why some stars host hot Jupiters but lack smaller rocky planets nearby. The giant planet moving inward through the disk of material may have scattered or absorbed much of the matter that would otherwise have formed terrestrial worlds. Super-Earths also challenge our understanding of planetary geology. On a planet with 2 or 3 times Earth's gravity, the behaviour of tectonic plates, volcanoes, and mountain formation could be very different. The thickness of the crust, the flow of the mantle, and the release of heat from the interior might follow patterns unfamiliar to us. There is also the question of atmospheres. A planet with stronger gravity can hold on to lighter gases more easily, potentially retaining thick envelopes of hydrogen or helium that would escape from a smaller world. This could lead to hybrid planets, partly rocky and partly gaseous, with deep atmospheres overlaying solid interiors. From a distance, such a planet might appear similar to a gas giant, yet beneath its clouds there could be a dense rocky surface under crushing pressure. Observing these worlds requires combining multiple techniques. By measuring a planet's mass through its gravitational effect on its star and its radius through transits, astronomers can calculate its average density. This in turn provides clues about its composition. A high density suggests rock and metal, a low density suggests gas or water. In some cases, atmospheric studies reveal the presence of hydrogen, helium, water vapour or other gases, adding further detail to the picture. Each measurement is a small piece of evidence, and together they form a portrait of a world that no one has ever seen directly. It is worth pausing to consider how remarkable this is. From faint signals in starlight, scientists can infer the size, mass, composition, and even aspects of the weather on planets hundreds of light years away. It is a quiet triumph of observation and reasoning, built on decades of careful work. Super-Earths and megaplanets also remind us that nature does not always produce tidy categories. There is no sharp line separating rocky planets from gas giants, or planets from brown dwarfs. Instead, there is a continuum, a range of possibilities shaped by initial conditions, formation histories, and the complex interplay of gravity, radiation, and chemistry. And as telescopes grow more powerful, we are beginning to explore this continuum in greater detail, discovering planets that fill in the gaps between familiar types, revealing new combinations of size, composition, and environment. These discoveries also influence the search for life. Some super-Earths orbit within the habitable zones of their stars, where temperatures might allow liquid water to exist. Whether such worlds are truly habitable depends on many factors, including atmospheric composition, geological activity, and magnetic fields, but their abundance makes them intriguing targets for future study. Not every planet orbits a star like our Sun. In fact, many of the most unusual worlds ever discovered circle stars that are themselves strange, faint, unstable, or even long dead. When astronomers first began finding exoplanets, most of the attention naturally focused on planets around Sun-like stars, because those systems seemed easiest to compare with our own. Yet as detection methods improved, it became clear that planets are not at all selective about their hosts. They form and survive in environments that once seemed far too hostile or unpredictable. One of the most surprising discoveries in the history of exoplanets came in 1992, before the famous detection of 51 Pegasi b, and before the flood of discoveries that followed. Astronomers studying a pulsar, an object known as PSR B1257+12, noticed subtle, regular variations in the timing of its radio pulses. Pulsars are extraordinary objects, the collapse cause of massive stars that ended their lives in supernova explosions. They are incredibly dense, packing more mass than the Sun into a sphere only about 20 kilometers across. As they rotate, they emit beams of radiation from their magnetic poles, and if those beams sweep past Earth, we detect them as pulses, arriving with remarkable regularity. The pulses are so precise that even tiny disturbances can be detected. When astronomers examine the timing variations carefully, they realize that they were being caused by planets orbiting the pulsar. Tugging gently on it, and altering the arrival times of the pulses, it was the first confirmed discovery of planets beyond our solar system, and it was not around a warm yellow star but around the remnant of a violent stellar explosion. It is difficult to imagine what such planets must be like. A pulsar emits intense radiation and powerful streams of charged particles. Any atmosphere on a nearby planet would be stripped away quickly, and the surface would be bombarded by high-energy particles. The sky, if there were one, would not glow with steady sunlight, but would be lit by brief, repeating flashes as the pulsar's beams swept overhead. These planets likely formed after the supernova, from debris that settled into a disk and gradually coalesced into new worlds. In a sense, they are second-generation planets, born from the ashes of a star's death. The idea that planetary systems can arise even after such catastrophic events is a reminder of how resilient and persistent the processes of formation can be. While pulsar planets are among the most extreme, they are also relatively rare, at least among the systems we have been able to study so far. Much more common are planets orbiting red dwarf stars. These stars are smaller and cooler than the Sun, and they make up the majority of stars in our galaxy. If you were to travel through the Milky Way, most of the stars you passed would be red dwarfs, faint and long-lived, burning their fuel slowly over trillions of years. Planets around red dwarfs present a different set of challenges and curiosities. Because these stars are dimmer, the region where temperatures allow liquid water to exist lies much closer to the star. Planets in this region often orbit at distances far smaller than Mercury's orbit around the Sun. As a result, many of them become tidally locked, showing the same face to their star at all times. We have already considered what life might be like on a tidally locked world, with permanent day on one side and endless night on the other. Around red dwarfs, this configuration may be especially common. The TRAPPIST-1 system, for example, contains 7 Earth-sized planets, several of which lie in or near the habitable zone. These worlds orbit so close to their star that their years last only a few days. Yet proximity to a red dwarf brings another complication. Many red dwarfs are highly active, especially in their youth, producing powerful stellar flares that release bursts of radiation. These flares can be far more energetic, relative to the star's size, than those produced by the Sun. A planet orbiting close by would be exposed to frequent surges of ultraviolet and X-ray radiation, which could erode atmospheres and pose challenges for any potential life. Astronomers are still studying how planetary atmospheres respond to such conditions. A strong magnetic field might help protect a planet, deflecting charged particles in the same way Earth's magnetosphere shields us from much of the solar wind. A thick atmosphere could also absorb some of the radiation, though it would likely undergo complex chemical changes as a result. Despite these challenges, red dwarf systems remain among the most promising places to search for habitable planets, simply because they are so numerous and their small size makes it easier to detect Earth-sized worlds in orbit around them. The dim light of the star also makes it easier to study the atmospheres of transiting planets. As the contrast between star and planet is more favourable, there are also planets orbiting stars much larger and hotter than the Sun. These stars burn brightly and live fast, consuming their fuel in a few 100 million years rather than billions. A planet in orbit around such a star would receive intense radiation and might experience dramatic changes as the star evolves rapidly, swelling into a giant and eventually shedding its outer layers. In such systems, the timescales for life to develop, at least in the way we understand it, might be very limited. Yet planets can still exist there, shaped by the same processes of accretion and gravitational interaction that operate everywhere in the galaxy. Binary star systems add another layer of complexity. Many stars exist not alone but in pairs, orbiting a common centre of gravity. Planets in these systems may orbit one star while the other shines in the sky as a brilliant companion, or they may orbit both stars at once, tracing a path around the pair. Such circumbinary planets, sometimes called Tatooine worlds after the fictional desert planet with 2 suns, have been discovered in several systems. The changing positions of the stars would produce complex patterns of daylight and seasons, with variations in illumination that could be quite dramatic depending on the orbital geometry. The gravitational dynamics of binary systems can also influence planetary orbits, sometimes making them more elliptical or causing subtle variations over time. Yet stable orbits are possible, and the existence of these planets shows that planetary systems can adapt to a wide range of stellar environments. White dwarfs, the dense remnants of stars like our Sun, present another unusual setting. After exhausting their fuel, such stars shed their outer layers and leave behind a hot, compact core about the size of Earth. For a time, the white dwarf glows intensely, gradually cooling over billions of years. Planets can survive this transformation if they are far enough away, and there is evidence that some systems contain planets or planetary debris orbiting white dwarfs. In a few cases, astronomers have detected the signatures of heavy elements in the atmospheres of white dwarfs, suggesting that asteroids or small planets have been torn apart and accreted onto the star. There is even speculation that new planets could form from the material shed during the star's final stages, though this remains an area of active research. Neutron stars and magnetars represent still more extreme stellar environments, though planets around such objects are rare and difficult to detect. The intense gravity and radiation make these systems challenging, places for planets to form or survive. Yet the discovery of pulsar planets reminds us that even the most violent events do not always prevent new worlds from emerging. Thinking about planets around exotic stars can shift the way we imagine the night sky. From the surface of such a planet, the star overhead might be a dim red ember, a brilliant blue-white sun, a pair of dancing lights, or a rapidly flashing beacon. The sky itself would reflect the nature of the star, shaping the colour of daylight, the pattern of seasons, and the energy available to the planet. It also highlights how adaptable planetary systems can be. Gravity, radiation, and chemistry operate everywhere, but the outcomes vary widely depending on initial conditions. A planet around a red dwarf may be tidally locked and bathed in infrared light. A planet around a pulsar may endure intense radiation under a sky that flickers with regular pulses. A world orbiting a binary star may see two shadows stretching across its surface. Each of these environments pushes the boundaries of what we consider normal, yet they're all natural consequences of the same physical laws. As astronomers continue to search for and study these systems, they are not only cataloguing new worlds, but also refining their understanding of how planets form and evolve under different conditions. The diversity of planetary environments suggests that the processes leading to planet formation are robust, capable of operating in settings far more varied than once imagined. And amid all these extremes, there remains a question that quietly follows every discovery. If planets can exist in so many different environments, some harsh, some temperate, some wildly unstable, then what are the limits of life itself? Could life adapt to conditions very different from those on Earth, or are there boundaries beyond which biology cannot persist? When people first hear about planets where iron may fall as rain, where oceans could be hundreds of kilometers deep, or where the surface glows with molten rock, the natural reaction is to assume that such places must be completely lifeless. After all, the environment seems so different from Earth that it is difficult to imagine anything surviving there. Yet the question of life in extreme environments is more complicated than it first appears, and exploring it requires us to look not only at distant planets, but also at the limits of life here at home. On Earth, life exists in places that would once have been considered impossible. Deep in the ocean, far below the reach of sunlight, entire ecosystems thrive around hydrothermal vents, where water heated by magma rises through cracks in the seafloor. The temperatures in these vents can exceed 300 degrees Celsius, and the pressure is immense, yet microorganisms not only survive but flourish, using chemical energy rather than sunlight as their primary source of power. There are also organisms that live in acidic lakes, in Antarctic ice, in salt flats where the water is almost too concentrated for cells to function, and even in rocks kilometers beneath the surface. These organisms, known as extremophiles, have adapted to conditions of heat, cold, pressure, radiation, and chemistry that would be lethal to most forms of life. The existence of extremophiles has gradually reshaped the way scientists think about habitability. Instead of asking whether a planet is exactly like Earth, researchers now consider a broader range of possibilities. What matters most is not whether conditions are comfortable for humans, but whether they allow complex chemistry to occur in a stable environment over long periods. Water is often considered one of the most important ingredients for life because it serves as an effective solvent, allowing molecules to interact and reactions to proceed. This is one reason that water worlds and planets in the habitable zones of their stars receive so much attention. But water alone is not enough. There must also be sources of energy and a supply of chemical elements such as carbon, nitrogen, oxygen, and phosphorus. On a water world with a deep global ocean, energy might come from geothermal activity, much as it does near hydrothermal vents on Earth. If the ocean is in contact with a rocky mantle, minerals could dissolve into the water, creating chemical gradients that microorganisms might exploit. Even if a layer of high-pressure ice separates the ocean from the mantle, some models suggest that fractures or localized melting could still allow exchanges of material. Rogue planets, drifting through interstellar space, might also host subsurface oceans if they retain enough internal heat and have thick insulating layers of ice. In such environments, sunlight would play no role at all. Life, if it existed, would rely entirely on chemical energy and heat from the planet's interior. Of course, these possibilities remain speculative. We have not yet found direct evidence of life beyond Earth, and the conditions required for life to begin in the first place are still not fully understood. Yet the discovery of extremophiles on our own planet has shown that life can adapt to conditions far more varied than once believed. When we turn to hotter and more extreme planets, the prospects become more uncertain. On a lava world where temperatures reach thousands of degrees, it is difficult to imagine any form of life as we know it surviving on the surface. Molecules essential for life would break apart at such temperatures, and any complex chemistry would be rapidly disrupted. However, even in such environments, there may be regions where conditions are less severe. On a tidally locked planet, for example, the terminator zone between day and night might offer temperatures moderate enough for liquid water to exist, provided the atmosphere is suitable. These narrow regions, sometimes described as twilight belts, could theoretically support stable climates, though this depends on many factors, including atmospheric circulation and pressure. Planets orbiting red dwarf stars present another interesting case. While stellar flares and radiation pose challenges, some models suggest that thick atmospheres or strong magnetic fields could protect the surface. In addition, the long lifetimes of red dwarfs, often trillions of years, mean that habitable conditions, if they exist, could persist for extraordinarily long periods, giving life ample time to develop. There is also the possibility that life might exist in forms very different from those on Earth. Most life here relies on carbon-based chemistry and liquid water, but scientists have speculated about alternative biochemistries. Some have proposed that life could use solvents other than water, such as methane or ammonia, under the right conditions. Saturn's moon Titan, with its lakes of liquid methane, is often cited as a place where such chemistry might be possible, though no evidence of life has been found there. Whether similar possibilities could exist on exoplanets remains an open question. The chemistry required for life is complex, and while alternative forms are conceivable, they remain theoretical. For now, most searches for life focus on environments where liquid water and carbon chemistry are likely to be present. One of the most promising methods for detecting life on distant planets involves studying their atmospheres. Certain gases such as oxygen, methane, and ozone can be produced by biological processes. If these gases are found together in certain proportions, they may indicate the presence of life, because they would otherwise react with each other and disappear over time. Space telescopes are now capable of analysing the atmospheres of some exoplanets, searching for these chemical signatures. The process is delicate and requires careful interpretation, because non-biological processes can also produce some of these gases. Nonetheless, it represents one of the most powerful tools we have for investigating the possibility of life beyond Earth. There is also a philosophical aspect to this search. When we ask whether life could exist on extreme worlds, we're really asking how adaptable life can be and how many different paths evolution might take under different conditions. On Earth, life has diversified into an extraordinary range of forms, from microscopic bacteria to towering forests and complex animals. Given enough time and suitable conditions, evolution tends to explore every available niche. If similar processes operate elsewhere, then life, if it arises, might adapt to environments very different from those on Earth. It might live beneath ice, in deep oceans, or in atmospheres rich in unfamiliar gases. It might rely on chemical reactions we have not yet observed, or exist in forms that challenge our definitions of what life is. At the same time, it is important to recognize that many extreme planets are likely to be completely sterile. Environments with intense radiation, extreme temperatures, or rapidly changing conditions may not allow complex chemistry to persist long enough for life to emerge. The universe is vast, and while life may be resilient, it is not necessarily inevitable. Yet even if most extreme worlds are lifeless, their study remains valuable. By understanding the full range of planetary environments, scientists can better identify the conditions that are truly favourable for life. Each extreme planet acts as a natural experiment, showing what happens when temperature, pressure, gravity, and chemistry are pushed to their limits. There is also something quietly inspiring about the idea that life, if it exists elsewhere, might be far more diverse than we imagine. The universe is older and larger than any one planet or species, and its history contains countless opportunities for complexity to arise. As astronomers continue to study exoplanets, they are not only cataloguing their sizes and orbits, but also searching for clues about their atmospheres, climates, and potential habitability. Each new discovery brings us a little closer to answering one of the oldest questions humans have ever asked. Are we alone? For now, the answer remains uncertain, but the search itself has already changed our understanding of the universe. We now know that planets are common, that environments vary widely, and that the conditions for life may be more flexible than once believed. When astronomers began finding planets around other stars, the first goal was simply to confirm that such worlds existed. For centuries, the question had been open, and the answer, once it arrived, was both simple and profound. Yes, planets are common. They orbit stars across the galaxy, in numbers far greater than anyone had imagined. But as the discoveries accumulated, something else began to emerge, something quieter and more reflective. These distant planets were not only interesting in their own right, they were also a mirror, showing us our own world from a new perspective. It is easy, living here, to think of Earth as ordinary. The sky above us feels familiar. Oceans, continents, weather, seasons, these seem like natural features of any world. Yet when we compare Earth to the planets we have been discussing, the differences become striking. Many exoplanets orbit so close to their stars that their surfaces glow with heat. Others are locked in eternal daylight on one side and endless night on the other. Some are shrouded in thick atmospheres of hydrogen or methane, while others drift alone through interstellar darkness. Against that background, Earth begins to look less like the default and more like an exception, a world balanced in ways that are not guaranteed to occur elsewhere. One of the most obvious lessons from extreme exoplanets concerns the importance of distance from a star. The habitable zone, sometimes called the Goldilocks zone, is the region where temperatures allow liquid water to exist on a planet's surface. Too close, and water evaporates. Too far, and it freezes. But the more planets we discover, the clearer it becomes that this zone is not a sharp boundary. Atmospheres, clouds, and greenhouse effects can shift the limits, making some planets warmer or cooler than their distance alone would suggest. Venus, for example, lies closer to the Sun than Earth, and has a thick atmosphere rich in carbon dioxide. The resulting greenhouse effect has driven its surface temperature to around 460 degrees Celsius, hotter than Mercury, even though Mercury is closer to the Sun. Mars, on the other hand, is farther out and has a thin atmosphere, allowing heat to escape easily, leaving it cold and dry. Studying extreme exoplanets helps scientists refine these models, improving our understanding of how atmospheres influence climate. By observing planets with thick atmospheres, thin ones, or none at all, researchers can test theories about heat transport, cloud formation, and atmospheric chemistry under a wide range of conditions. Another lesson involves planetary mass and gravity. A planet's size influences its ability to hold an atmosphere, retain heat, and sustain geological activity. Too small, and the atmosphere escapes into space, as happened on Mars. Too large, and the planet may accumulate a thick envelope of gas, becoming more like a mini Neptune than a rocky world. Earth sits in a range that allows it to maintain an atmosphere without becoming a gas giant, to retain internal heat without remaining geologically unstable for too long, and to support liquid water over billions of years. Observing super-Earths and mini-Neptunes shows us how small changes in mass can lead to very different outcomes. There is also the role of magnetic fields. Earth's magnetic field, generated by the motion of molten iron in its outer core, deflects charged particles from the Sun, protecting the atmosphere from erosion. On planets without such protection, stellar winds can gradually strip away the atmosphere, as appears to have happened on Mars. When astronomers study exoplanets around active stars, particularly red dwarfs, they pay close attention to this factor. A strong magnetic field could be crucial for long-term habitability, especially in environments where stellar radiation is intense. Extreme exoplanets also remind us of the importance of geological activity. Plate tectonics, volcanism, and the cycling of carbon between the atmosphere and the interior help regulate Earth's climate over long timescales. Without these processes, carbon dioxide might accumulate uncontrollably or disappear entirely, leading to runaway greenhouse or icehouse conditions. On many exoplanets, especially those larger than Earth, the behavior of the interior may differ significantly. High gravity could suppress plate tectonics, or thick atmospheres could alter surface conditions. By studying such planets, scientists can better understand the range of geological processes that might occur and how they influence climate. Another factor that becomes clear when comparing Earth to extreme worlds is the role of a stable orbit. Some exoplanets follow highly elliptical paths, experiencing dramatic temperature swings as they move closer to and farther from their stars. Earth's orbit is relatively circular, providing a stable climate over long periods. This stability may have been important for the development of complex life. There is also the influence of a large moon. Earth's moon helps stabilize the tilt of our planet's axis, preventing large, chaotic shifts that could lead to extreme climate changes. Not all planets have large moons, and the absence of such stabilization could produce environments very different from our own. These considerations lead to a broader realization. Habitability is not determined by a single factor, but by a combination of many conditions working together. Distance from the star, atmospheric composition, planetary mass, magnetic field, geological activity, orbital stability, and even the presence of moons all play roles. Extreme exoplanets help illustrate what happens when one or more of these factors is pushed beyond familiar limits. They are not merely curiosities, they are experiments conducted by nature, showing us the range of possible outcomes. There is also a deeper lesson, one that has less to do with physics and more to do with perspective. For most of human history, Earth was assumed to be the centre of the universe, or at least uniquely suited for life in a cosmos otherwise empty. The discovery of other planets, first in our solar system and then around other stars, gradually changed that view. Now, as we find thousands of exoplanets, we see that Earth is one world among many, part of a vast and diverse population. Yet this realization does not diminish the value of our planet. If anything, it enhances it. By comparing Earth to extreme worlds, we see more clearly how unusual our balance of conditions may be. Oceans that remain liquid over billions of years, a climate moderated by atmosphere and geology, a magnetic field shielding the surface, a stable orbit around a relatively quiet star. Each of these factors contributes to an environment where life not only began but flourished and evolved into complex forms. This does not mean that Earth is unique in the universe. There may be many planets with similar conditions, but it does remind us that such conditions are not inevitable. They are the result of many variables aligning over long periods of time. Studying extreme exoplanets also helps us understand the future of Earth. Some of the processes observed on other worlds may eventually occur here, though on timescales far longer than human civilization has existed. The sun will gradually grow brighter over billions of years, increasing the temperature of Earth and eventually evaporating the oceans. Venus may represent a possible future state of our planet, though far in the future. Understanding how atmospheres evolve, how greenhouse effects operate, and how planets lose water to space provides insights into these long-term changes. In this way, exoplanet research is not only about distant worlds, but also about the long-term history of our own. There is also an emotional aspect to this perspective. Seeing Earth from afar, as astronauts have described, often produces a sense of fragility and connection. The planet appears small, blue, and alone in the darkness, its thin atmosphere a delicate veil protecting the surface. Extreme exoplanets reinforce that impression. They show us how harsh most environments can be, how rare temperate conditions may be, and how remarkable it is that life has found a home here. At the same time, they expand our sense of possibility. The universe is not limited to one type of planet or one set of conditions. It contains worlds of fire, ice, water, darkness, and storms, each shaped by the same physical laws yet expressing them in different ways. This diversity invites curiosity rather than fear. It encourages us to explore, to observe, and to continue asking questions about how planets form, how they change, and how life might arise under different circumstances. And as telescopes become more powerful and new missions are launched, we are likely to discover even more surprising worlds, planets that challenge our assumptions in ways we cannot yet predict. Each discovery will add another piece to the picture, another example of how varied the universe can be. Yet through all these discoveries, one thing remains constant. We are observers, looking outward from a small planet, using light that has travelled across immense distances to understand places we may never visit. There is something quietly humbling about that, a reminder of both our smallness and our capacity to learn. Now, after wandering through lava seas, endless storms, silent oceans, and worlds that drift alone between the stars, it can feel natural to slow the pace a little and simply sit with the scale of what we have been considering. The universe is vast in a way that is difficult to grasp all at once, and sometimes the most comfortable way to understand it is not through numbers or distances, but through quiet imagination. If you pause for a moment and picture the night sky, not as a chart of constellations, but as a real, physical place, it begins to feel different. Every point of light is a star. Around many of those stars are planets. Around some of those planets are moons, atmospheres, clouds, storms, oceans, and landscapes shaped by gravity and time. And between all of those systems lies an enormous darkness, not empty in the sense of nothingness, but spacious, calm, and patient. It is interesting how the mind responds to that idea. At first, the vastness can feel overwhelming. Distances between stars are so great that even light takes years to travel from one to another. Journeys on human timescales seem almost impossible. Yet after a moment, that same vastness can begin to feel peaceful instead of intimidating. The universe is not crowded or hurried. It unfolds slowly, on timescales so long that even mountains and oceans seem temporary. Extreme exoplanets, in their own way, help us feel that calm perspective. They remind us that the universe is not limited to one pattern or one familiar kind of world. It is creative in a quiet, unhurried way, forming planets of many sizes, temperatures, and compositions, allowing them to evolve over millions or billions of years. There is also something comforting in the realization that the laws of physics are the same everywhere. The same gravity that holds you gently to the surface of Earth shapes the orbits of planets around distant stars. The same chemistry that allows water to flow in rivers here determines the behavior of oceans on worlds we may never see directly. The same light that warms your skin on a sunny day travels across interstellar space, carrying information about distant atmospheres and clouds. In that sense, the universe is both vast and connected. The processes we observe here are not unique. They are part of a larger pattern, repeating in countless variations across the galaxy. Another thought that often arises when considering distant worlds is the question of time. The light from many of the stars we have been discussing began its journey long before modern cities existed, long before electricity or flight, sometimes even before written history. By the time that light reached telescopes on Earth, the planets it illuminated may already have changed. Storms may have moved, atmospheres may have shifted, orbits may have evolved. We are always seeing the universe as it was, not as it is in this very instant. There is something quietly poetic about that, though perhaps poetic is not quite the right word. It is more a sense of continuity, of events unfolding over immense spans, connected by the steady movement of light. If you imagine standing on one of those distant worlds, perhaps on the twilight line of a tidally locked planet, or on the frozen surface of a rogue planet beneath a sky filled with stars, the sense of time would feel different. Days might be shorter or longer, or absent altogether. Seasons might not exist. The familiar rhythms of sunrise and sunset that guide life on Earth would be replaced by other patterns, or perhaps by none at all. And yet, even there, time would still pass in the same quiet way. Atoms would vibrate, heat would flow, light would travel. The fundamental processes of the universe would continue, steady and unhurried. It is also worth reflecting on how much our understanding of these worlds has grown in such a short time. Only a few decades ago, the existence of planets around other stars was uncertain. Now we know of thousands, and the number continues to grow each year. Telescopes have become more sensitive, techniques more precise, and our ability to interpret faint signals has improved remarkably. This progress did not happen all at once. It came through patience, through careful observation, and through the gradual accumulation of knowledge. There is something reassuring about that pace. Discovery does not always require urgency. Sometimes it unfolds quietly, one observation at a time. The study of extreme exoplanets has also changed the way we think about our own place in the universe. Earth is not the centre of everything, nor is it the only world where interesting processes occur, but neither is it insignificant. It is one example among many, and a particularly gentle one, a place where conditions allow life to flourish, and where a species has emerged capable of looking outward and asking questions. That ability to ask questions may be one of the most remarkable things about our planet. The same atoms that form rocks and oceans have arranged themselves into minds capable of curiosity. We are part of the universe studying itself, in a quiet and indirect way. Sometimes, when thinking about distant worlds, people wonder whether we will ever visit them. The distances are so great that such journeys remain far beyond our current technology, and perhaps they always will be. Yet there is another way of travelling, one that does not require spacecraft. Through observation, imagination, and understanding, we can explore these places in our thoughts, building pictures of landscapes and skies from the faintest traces of light. That kind of exploration is slower, but it has its own kind of richness. It invites patience and reflection rather than speed. As you listen now, wherever you happen to be, you might notice the quiet around you. Perhaps there is the faint hum of a distant sound, or the gentle rhythm of your own breathing. The same calm that exists in this moment exists in a different way across the vast distances of space. Stars burn steadily. Planets orbit in silence. Light travels without hurry. It can be comforting to think of the universe as a place not of constant drama, but of long, gentle processes unfolding in their own time. And that brings us back, in a quiet circle, to the sky above Earth. Tonight, somewhere above the clouds, the stars are shining as they always have. Around many of them, unseen planets continue their journeys, some hot, some cold, some dark, some bright, each following its path through space. You are here, on one of those worlds, listening, thinking, perhaps beginning to feel a little more relaxed than when this journey began. Time has passed, though it may not feel like it. Thoughts have drifted, perhaps slowed, perhaps settled. Before we end, let me gently ask you something. The same kind of quiet question that helps anchor us in the present. Where are you listening from tonight? And what time is it there right now? It is interesting to think that while we have been imagining planets thousands of light years away, each of us is in our own place, at our own hour, sharing this small moment of calm. If you found this journey peaceful or interesting, I would be grateful if you considered liking the video or subscribing so that more people can find these quiet explorations and take a few moments to rest their thoughts. But for now, there is nothing else you need to do. Just let the ideas settle, the way ripples fade on the surface of water. Somewhere far beyond our sky, planets continue to turn in darkness and light, in silence so complete that even storms make no sound in the vacuum between worlds. And here, on this small blue planet, night continues in its gentle way, carrying you steadily forward, one quiet moment at a time.